So with that, we welcome Professor Masaki Oshikawa from the University of Tokyo for the second talk of the day. Masaki will tell us about the measurement-induced entanglement between quantum spin chains.
Okay. Yeah, thank you, ma'am. And I'd like to thank first to the organizers for kindly inviting me here and giving me the opportunity to speak. And it's very nice to come back to ICTS, which I like very much. And actually this photo is from my last visit 4 years ago. Maybe many of you might know, so this is a Hesaragata Lake, just 4 or 5 kilometers from here. And I went there with my bike. There's a nice temple. And somehow on that particular day, the sky was completely blue. So, okay. So actually, I'm sorry I missed the first day, Monday of this meeting, and also maybe first session of Tuesday, because I had to go to a memorial meeting for Ian Affleck, who was my postdoc advisor, who unfortunately passed away last month, October 4th. I really learned a lot from Ian, and not only physics, but he liked hiking, cycling, and everything. So he took me and many of other physicists to hiking many times. And this was one of my photos, Ian, on hiking near Vancouver. So he was very fit, and he was maybe 15, 16 years senior than me, but still I was always struggling just to follow him on hiking. So I still cannot kind of believe that he passed away so early. But anyway, so I have many memories about Ian, so I'm trying to write up something. So if you are, this is still in work of progress, but if you are interested, you can check here. And I'm also talking with few other colleagues to make some special memorial issue for Ian, which you might want to contribute. So if I cannot announce the details yet, but if you are interested, please contact me. And so actually, I went to Vancouver as Ian's postdoc back in '95. And this is my first project with Ian. I mentioned something to Ian, then Ian immediately suggested this problem. So this was a defect line in the critical Ising model. So critical Ising model is, of course, very, very understood in terms of conformal field theory and everything. But you can also introduce some defect line, like changing the coupling constant along some line. And so the defect doesn't look like a boundary, but if you follow the system at the defect, then the defect becomes a boundary, and now the bulk becomes a double layer Ising model. So the defect in the Ising model can be regarded as a boundary of double layer Ising model, which is a special point of Ashkin-Taylor model. So by using, applying the boundary conformal field theory technique to this problem, we could obtain many results. So this was my first paper with Ian, and I later published a full paper in Nuclear Physics B. And so this kind of problem is now regarded as maybe the simplest case of so-called conform defect. So these days, many people, high energy physics, field theory, are interested in defect in conformal field theory and so on. So this is a citation statistics of my paper with Ian. So after the publication, maybe not much, but it's recently kind of becoming a hot subject. So it's not bad. Okay. And so this is the city of Vancouver, where Ian lived and I lived. Actually, UBC is to the left of this map. But anyway, so this is the downtown. So this is the area originally developed. But there is also some area north to the Vancouver, and there are mountains. So this is also a nice area. But this was more later developed. So if you allow me, maybe this is like quantum many-body physics, more traditional area of physics, and this is like a quantum information, relatively new area of physics. And I think the theme of this workshop is to connect these fields to different fields. So we want to go back and forth, but there is an inlet. Actually, this is also part of continent. This is also part of continent, but this is a very long inlet, maybe 50 kilometers or more. And there are also a lot of mountains. So if you avoid this inlet and drive, then you have to drive like, I don't know, 400 kilometers or something to reach this North Shore. That is inconvenient. So we need something to go back and forth. And fortunately, we have bridge, actually 2 bridges. So this is a Lion's Gate Bridge, which looks nice from below. And importantly for me, you can also cross this bridge by bicycle. Okay. So yeah, we need something to connect these two. And in case of quantum many-body physics and quantum information, of course, there are many connections. But in this talk, I want to focus on one connection, which is boundary conformal field theory, which I learned from here. So actually, my main scientific content of my talk is based on this recent preprint with Ashida-san and Hoshino-san. Actually, Hoshino-san is a first-year grad student of Ashida-san. Ashida-san is a young faculty in physics department of University of Tokyo. Actually, the title of my talk says measurement-induced entanglement, but the title of this paper says entanglement swapping. I changed the title a little bit because perhaps quantum information people know about this entanglement swapping. But actually, this was my first time seeing this entanglement swapping. So perhaps most of condensed matter colleagues are not familiar with this word. So first, let me explain what is this entanglement swapping. So I just copied this figure from this recent paper. So there are 4 guys, or 4 qubits, Alice and Bob and Kara and Danny. And so Alice and Bob have entangled qubit between these two. And Kara and Danny also have entangled qubit between these two. And because they are, each of these pairs are maximally entangled, so there is no entanglement between these two. But now you can perform the measurement in Bell pair basis, that is maximally entangled basis between these two, Bob and Kara. Okay. That is, you project onto one of the 4 maximally entangled states. Then after the measurement, projective measurement, the qubit of Bob and qubit of Kara are now maximally entangled. But I didn't do anything about on the qubit of Alice and qubit of Danny. But the interesting thing is that after this projective measurement, now the qubit of Alice is maximally entangled with qubit of Danny. So this is called entanglement swapping, because initially you had only entanglement between these two and these two, but after the projective measurement on this pair, now these ones are entangled. That is, of course, natural, but not only this pair, but this pair is also now entangled. So this is called entanglement swapping. Yes? Mm-hmm. Yeah. So you project on one of the maximally entangled state, like a 0, 1 plus 1, 0. So, okay, so this is, it's me. Very interesting, but simple problem. So in this talk, what I want to discuss is many body version of this entanglement swapping, or I could say measurement-induced entanglement. So this is our setup. So I have two independent spin 1/2 XXZ chain, which already appeared several times in this workshop. And each of these spin 1/2 XXZ chains is in the ground state. So initially this chain is in the ground state and this chain is in the ground state. Then there is no entanglement at all between these two. And now we split this chain or ladder, if you like, into two regions. And in one region, you do this bell pair measurement between this spin and this spin, and this spin and this spin, and this spin and this spin, and this spin and this spin. So after the measurement, of course, this measured pair is projected onto one of the bell pair states, so they are maximally entangled. But I don't touch these spins at all. But similarly to the entanglement swapping I described in the previous slide, after doing this measurement, this part of spin chain and this part of spin chain are now entangled. Because before the measurement, this part of spin chain was entangled with this part, and this part of spin chain was entangled with this part. But now you kind of impose the entanglement between these two regions by projective measurement. So now, after the measurement, this part of the spin chain and this part of the spin chain must be entangled. And yes. It shouldn't matter, I think. But you can have many different outcomes of the measurement, which can matter in principle. So, okay, so this is set up, and what I want to do now is to quantify the entanglement between this section and this section of spin chain in terms of, let's say, entanglement entropy. Yeah. Yeah, yeah. Depending on that outcome, which entanglement they have to apply some numerical. Oh, well, I think the entanglement, for example, the entropy is the same, but yeah, I think that depending on measurement outcome, the exact state, yeah, different. Yeah, to how to say, to make the, to obtain the really same state, I think, yeah, you need to apply some correction. Yeah. Okay, so this is a setup, and yeah, I want to formulate this problem. And yeah, this, I think, also discussed in this workshop. So for this spin 1/2 XXZ chain, which is integrable, but also the low energy physics can be described by powerful formulation of Tomonaga-Lattinger-Rigid or free boson conformal field theory. So effective Lagrangian is like this, very simple free boson. And each of these spin operator admits this field theory representation. And because we start from two independent XXZ chains, we can bosonize each chain. So the entire system is represented by two component free boson field theory. For example, phi 1 for chain 1, and phi 2 for chain 2. Then I want to perform this bell pair measurement, which is a projective measurement to one of 4 bell pair states. So bell pair state is usually defined like this. So it's labeled by 2 binaries, B1 and B2. Each of them is 0 or 1. And the very pair state is defined like this. For example, 0, 0, one of the very pair states, 0, 0, is given by 0 and 0. So you have 0, 0. And 1 and the B1 bar means the conjugate of B1. So if B1 is 0, then you must choose here 1. And the minus 1 to power of B2 is 1 for B2 equals 0. So Bell pair state for 0, 0 is a superposition of 0, 0 and 1, 1 with plus sign. And in magnetism language, spin language, we can identify 0 with up spin and 1 with down spin. And this is the up, up plus down, down. So one of the triplet state. And you can find 3 other Bell pair states in a similar way. Then suppose you did a measurement, and suppose you get the outcome 0, 0. And after the measurement, your pair of spins must be in this particular state. But that means that the sigma z takes the same value for chain 1 and chain 2 at that location of measurement. But the sigma z has this expression. So there are 2 contributions, uniform term and the alternating term. But this alternating term is more dominant. So basically, cosine of 2 phi takes up the same value between chain 1 and chain 2. So this can be regarded in terms of field theory. Basically, phi 1 from chain 1 and phi 2 from chain 2 must have the same value. So measurement and the outcome 0, 0 is basically imposing this condition, phi 1 minus phi 2 equals 0, locally at the place of the measurement. And similarly, so this is one of the triplet states. So the total Sx for these 2 spins actually turns out to be plus 1. And by imposing this condition, total spin x to x component of spin of these 2 spin 1 halves to be plus 1, by looking at this bosonized expression of spin operator, we can also find that phi 1 plus, theta's dual field to phi, and the theta 1 plus theta 2 must be 0. If you obtain this outcome 0, 0 at the place of measurement. So the outcome of measurement can be replaced by this local boundary condition in terms of field theory. Then, as I mentioned, in principle, every time you measure, you don't know the outcome. So you can obtain one of the 4 outcomes, 0, 0, 0, 1, 1, 0, 1, 1, randomly. Although, actually, it's not completely random. There must be some correlation, but a priori, you don't know which outcome you obtain. But to simplify my analysis, I first consider a very special case, which I might call a forced measurement, or, well, you can consider this by post-selection. But anyway, so you measure a pair of spins in this green region. And suppose that you obtain the same outcome every time, 0, 0. For every measured pair of spin, you obtain 0, 0. That's a situation I consider. Of course, that's very special situation, and it can happen only with very small probability, but still we can consider this situation to start. Okay. Then in this case, in this green region, at every point you measure, you obtain 0, 0. So I want to impose the boundary condition I introduce. Phi 1 equals to phi 2, and theta 1 plus theta 2 equals 0. That's one of the Dirichlet type boundary condition on this green region. But this purple region, I didn't touch. So in this region, the field remains free. And of course, this measurement is done on at the level of quantum state of wave function. But because you start from the ground state, and in terms of path integral, so this is also a common trick, but in terms of path integral, this ground state wave function can be identified as a cross-section of a path integral with an infinitely long cylinder. You start from imaginary time minus infinity and do the imaginary time evolution, then only the ground state survives. So you can imagine infinitely long half cylinder and consider the cross-section. Then at the cross-section, you have the ground state. Then you do the measurement, and because of the measurement outcome, you impose some boundary condition here. Then this unmeasured section remains free. Then I want to compute the entanglement entropy between two chains in this region, which can be computed by this standard replica trick. So I consider n replicas of this same system, and then consider the reduced density matrix on this purple area, and then take the trace of nth power of the density matrix for this purple region. Then by taking nth power of rho means that I want to connect the ket of j's replica to bra of j plus first replica. So in order to calculate this partition function, I also impose some boundary condition between replicas on this purple region. And in green region, I impose a boundary condition coming from the measurement outcome. So in this way, the problem of calculating this partition function is reduced to the problem of the boundary partition function, or partition function of a boundary conformal field theory for this free boson field theory. Okay, so this is a problem, but in order to do this, I had to go back to the more standard and very well-known problem in CFT, that is entanglement entropy in conformal field theory between a finite length segment and the rest of the system. So suppose you have an infinitely long conformal field theory, a ground state wave function, and consider the finite length segment of length L. And you consider the entanglement entropy between this red section and the rest of the system. And this is very standard problem with CFT, and you can find this in many textbooks or reviews. And this result, so this is a result. C is the central charge of CFT, and C over 3 times log of this length, plus some constant. And in condensed matter community, this formula is often called as Calabrese-Cardy formula, but actually before that, in 1994, Holzer and Wilczek derived this formula originally. Of course, Calabrese-Cardy did many systematic generalization. Anyways. And this is this first paper by Holzer, and Wilczek in 94. And this is very well-known formula. And of course, I went through Calabrese-Cardy paper several times. But this was one of the results which is certainly very important, but I didn't really understand by heart, which means that often students ask me like, how to derive this formula. Then I would answer like, well, you can look Calabrese-Cardy. So I, kind of escaped from the question. Yeah, something, if you ask me, I can just go to Blackboard and explain everything. But this was not one of those formula in my part. But because this time I had to think about this measurement-induced problem, I had to think about this formula again. And now I have better understanding. So it's, of course, if I look back, it's completely discussed in this paper, but in a way concealed, at least for me. So let me share my current understanding of this famous formula. But before going into this, scientific derivation, I want to mention about these authors of this very important paper. And of course, perhaps I need no explanation about Frank Wilczek, who is, Nobel laureate and asymptotic freedom, and more recently, proponent of this time crystal and so on. And honestly, I didn't quite know this Finn Larsen, second author, but because he has been working mostly in high energy physics, field theory. But anyway, he is now professor at University of maybe Michigan or something. So anyway, yeah, he has been doing well in physics, successful career. But there was a first author, Chris Halsey, whom I didn't know. So I Googled about him. And indeed, I found him. He's still in academia. Okay, so this is the guy, the first author of this entanglement entropy paper. So he's now director, but the director not in Physics Institute, but the Institute of Cultural Identity or something in Berlin, Germany, because he did a PhD in Princeton with Frank Wilczek. But after finishing PhD, he somehow went to grad school again, master's and PhD in German literature, okay, in Columbia University. So he went to German literature or some German philosophy. And now he's director of this institute doing, I don't know, literature or philosophy. So so he seems to be a very successful person. And also, I think it's kind of interesting life, During PhD, you wrote an important paper in physics and then completely switched the field and now doing philosophy or literature and also successful in that. Anyway, so back to physics. So in order to derive this famous entanglement entropy formula, first I need to define this reduced density matrix. So you start from the ground state of CFT psi 0. Then you take the trace for degree of freedom outside this red region, partial trace. Then you define this rho A. Then consider the nth power of this reduced density matrix, then take trace. And then take logarithm, then divide by this 1 minus n, which defines the Renyi entanglement entropy. And this can be computed by replica trick for n positive integer. But after that, you regard n as a real parameter and take the limit of n goes to 1, then you can compute the von Neumann entanglement entropy. So this is a standard replica trick. And again, I apply the same technique. So you start from the path integral of bulk CFT on infinity long cylinder or something, starting from imaginary time minus infinity, and do the imaginary time evolution, and consider the cross section at tau equals 0, then you find the ground state. Then you impose the, first you take the trace outside this red region. To do that, you prepare the Bra copy of the field theory and Ket copy of the field theory. And if you identify Bra and Ket, then you are taking a trace. But on this red region, you don't do this. But instead, you take nth power of this reduced density matrix and then take trace. Means that you prepare n replicas and you identify Ket field of J's replica with a Bra field of J plus first replica. So this is like imposing, taking this trace. So that means that you prepare actually 2n copies of the field theory because you have n replica, but for each replica, you must have Bra and Ket. So you prepare 2n copies of the same CFT and impose on blue region and this boundary condition on red region. Then compute a partial function. But again, this is a standard setup in boundary conformal field theory. And in particular, you impose different kind of boundary conditions here and there, which means that the boundary condition changes at this point and this point. And in terms of boundary conformal field theory, this can be identified with insertion of so-called boundary condition changing operator. So in this view, this boundary partition function I want to compute can be regarded as a two-point function of a boundary condition changing operator, sometimes called a twist operator. And in this way, this correlation function must be given by 1 over the distance or segment length to the power, and this power is exactly given by twice the scaling dimension of this boundary condition changing operator. So the problem is reduced to finding the scaling dimension of this boundary condition changing operator. And there is a general prescription in boundary conformal field theory to find such scaling dimension. That is, initially, we are considering the setup like this. Boundary condition changing operator was here and there. But you can do the conformal mapping and send one of these points to minus infinity and send the other boundary condition changing operator to plus infinity. Then this half plane can be conformally mapped to infinitely long cylinder. And the boundary condition changing operators are now in the minus infinity and plus infinity. So in this way, you have a strip with boundaries on both sides. And on one side of the boundary, you impose a boundary condition A alpha bar, which is a blue boundary condition. And on the other side of the boundary condition, you have boundary condition alpha and red boundary. And in this way, the scaling dimension of the boundary condition changing operator is related to the ground state energy of this strip, or ground state energy in the sense that you can consider time evolution, imaginary time evolution in this vertical direction. Then ground state energy is related to the spectrum, the transfer matrix in this vertical direction. So you compare the ground state energy of the Hamiltonian with two different boundary conditions, alpha and alpha bar on both sides, and then you can find the ground state energy. Then you compare this with the ground state energy with the same boundary conditions, alpha bar on both sides. And you subtract, then this is related to the scaling dimension of the boundary condition changing operator. So this is a standard procedure in boundary CST. And so I just need to find the ground state energy for those combinations of the boundary conditions. But now I can relate this problem to, yes?
This procedure that you just mentioned, remember the trace energy?
Yeah, of course, everything must be equivalent, yeah. But at least for condensed matter people, this is a very familiar procedure, yes. Okay, and so now I need to compute the ground state energy for particular combination of boundary conditions. But for this particular setup, I can reduce this setup to very familiar situation. That is, we started from open strip with some boundary condition. But in this boundary condition alpha bar, you identify Bra and Ket field within same replica. But on the other side of the boundary, you identify Ket field of J's replica with a Bra field of next replica. So, for example, you start from J's Bra field and then hit the left boundary. Then you are smoothly connected to J's replica Ket field, and then reflected back, and eventually reach the right boundary. But at the right boundary, this J's Ket field is smoothly connected to Bra field of J plus first replica, then reflected back to the left. Then when you hit the left boundary, again, your Bra field is smoothly connected to Ket field of the same replica. So if you go back and forth, then you started from 2n copies of the same conformal field, phi, because n replica and the Bra and Ket. But going back and forth, actually every component is smoothly connected. So you end up with single field, conformal field theory, but with a periodic boundary condition. So on a ring, but the circumference of ring is actually given by 2n times L, because you need to go back and forth to scan all the components. So the ground state energy for this particular boundary condition is nothing but the ground state of system on the ring with a periodic boundary condition. Very familiar problem for in condensed matter physics. But circumference is 2n times L. But you need to compare this ground state energy with this alpha bar boundary condition, in which case at each boundary, bra and ket are connected, but within same replica. So in this case, again, you can map this problem to the conformal field theory on a ring with periodic boundary condition. But you can form the ring just by going left and right. So the circumference of ring is now 2L. But now n replicas are completely independent, as it should. So the ground state energy for this boundary condition is n times this. Oh, okay. So, and by the way, this is another very well-known formula of the ground state energy of conformal field theory on the ring, which was first derived by Bhattacharjee, Nightingale, and Ian Affleck in 1986. So yeah, so these are original papers. By the way, if perhaps you might know, but this formula was independently derived by this group of people and Ian Affleck in 86. So these two papers were published back to back in PRL in 86. So yeah, so actually perhaps you are familiar with this result. I knew this formula for a very long time, but now this formula looks very natural because this 1 over n comes from this ring of circumference 2nl. And this factor n comes because you have a ground state energy of n copies of the same CFT. So anyway, by computation of this ground state energy, I can derive this scaling dimension of the boundary condition changing operator. And I can plug this in, then I can obtain the Renyi entanglement entropy of the finite section of CFT. And by taking the limit of n goes to 1, I can reproduce this result. Okay, so as I said, okay, so essentially this derivation was already contained in the original paper, but at least in a not so clear form to people like me. But now I can connect this to another very well-known formula in CFT. So what I wanted to say was that, so in quantum condensed matter physics, this Bhattacharjee, Nightingale, Affleck formula, universal correction to the ground state energy of CFT has been very, very well known. And in quantum information, this entanglement entropy formula were very, very well known. But by using this argument in standard and boundary CFT, actually, I can directly derive this formula from the other important formula. So, okay, I spent maybe too much time on a very well-known result, but I still did this because once I understood that formula in this way, then actually it's kind of easy to apply similar technique to this measurement-induced entanglement swapping problem because it's very similar. So you impose some boundary condition due to measurement outcome, and here you still have free, but you connect replicas together in replica trick. So again, this boundary partition function is related to the scaling dimension of the boundary condition changing operator here and there, which are different from this Holtze-Larsen-Wilczek formula operator, but in a sense very similar. So we can use a similar trick. And yeah, if you apply similar trick, you can easily find that this scaling dimension of this boundary condition changing operator is given by n over 6 minus 1 over 24n. and you plug in, then you can find the boundary partition function, then derive the linear entanglement entropy, and then taking replica limit n goes to 1, you can derive this formula. So this is entanglement entropy between two unmeasured sections of spin chains. And it's similar to this very famous formula, Larsen-Wilczek, but the coefficient is different. So it was generally C over 3. So for free boson field theory, C equals to 1. So it was 1/3. But in a sense, this coefficient is basically just halved to 1/6. So this is a CFT result I can derive, at least for very special outcome. But this Hoshino-san, the student, was doing a very thorough numerical calculation. So there is some even odd effect, but at least on average, his numerical result fit with this conformal field theory formula very well. And he extracted this coefficient numerically, but the coefficient was like 0.166, 168, and 170, which are pretty close to 1/6, which is 0.1666. And I want to say that they obtained this result before our doing this boundary CFT derivation. So it's not, I think these estimates were not biased. And from CFT, this is pretty robust. And actually, this is independent of so-called Latinger parameter or this compactation radius. So, okay, and linear independence also matches reasonably well. And one thing I have to say is that so far, my boundary CFT derivation is limited to this very special outcome, that is uniform outcome, which is certainly very special. But if you can do this kind of experiment, as I said, every time you can have a different outcome. And more physical or realistic quantity is the entanglement entropy after obtaining some many different outcomes, and you average over all the possible outcomes. And that I still cannot calculate from CFT at this point. But Hoshino-san did numerical calculation, numerical averaging over all possible measurement outcome, which is more challenging numerically, but at least for smaller system he can do. And interestingly, at least within numerical precision, this entanglement entropy after averaging looks pretty much same or similar to previous result for uniform, very special outcome. So maybe after averaging, after all, we might get the same result. Maybe some small correction, which I don't know yet. Okay, so this is still a challenge for theory, because for theory, typical outcome contains many different outcomes, then it corresponds to insertion of many boundary condition changing operator, which is more challenging to calculate. But the numerics indicates that after averaging, the result looks similar. Okay, and I have to say that they also tested Ising case, but the result sometimes doesn't look like a conformal invariant, so this is still mystery. Okay, so yeah, this is a summary. So yeah, this boundary CFT works as a bridge between quantum many-body physics and quantum information. And for this very specific program, it seems to work, at least for the special outcome. But even after averaging, the result seems to be similar. But there are also many open problems which, I want to discuss and explore. Thank you very much.
Thank you, Masaki, for a very nice talk. So I think we have time for some questions, comments.
So you are showing the entanglement that is created between the two spin chains.
Yeah, yeah.
So what happens, do you know, if you just look at the entanglement along a spin chain rest?
Oh, so you mean, so after the same kind of measurement, you're asking the measurement between, for example, this part of spin chain and the other. Yeah. Well, short answer is I haven't studied, so I don't know. But Yeah, maybe we can combine these two derivations to see some result. Okay, I don't know yet, but that may be doable. Yeah, thank you.
Regarding the observation that if you average your measurement outcomes, you get the same result. Isn't it true that distinct Bell measurements are related to each other by local unitary transformation?
Yeah.
So is it not unsurprising that as a result all the measurement outcomes are related to each other?
Okay. So what I can say is that there are 4 possible outcomes. So as long as you obtain the same result, uniform outcome everywhere, it doesn't matter whether it's 0, 0 or 0, 1 or 1, 0 or 1, 1. But you can have 0, 0 here and 1, 0 here, 1, 1 here. Then in that case of mixture of different outcomes, from CFT point of view, I need to insert boundary condition changing operator whenever you meet a different outcome. So it seems like a more non-trivial correlation function. But okay, maybe you can find a clever argument that why or the outcome doesn't matter, maybe. But at least for me, it looks like a more non-trivial problem. But maybe you are right.
We can talk later.
Very naive question. Can you go to this picture of 2 chain? No, you have shown. No. Yeah. So the question is, in the first chain, there is some entanglement between A prime versus rest. And second chain also there is some entanglement versus A versus rest. On the rest part, you want to do this Bell basis measurement, and finally want to see the entanglement between this unmeasured part. That is the aim.
Right.
Okay, I'm saying intuitively because I don't know all these things. So in A prime, first chain, A prime versus rest has some amount of entanglement.
Yeah.
And in the second chain also, A versus rest some amount of entanglement.
Yeah.
The unmeasured part, final entanglement generated, that will be at least minimum of these two. That should be the case, no? Intuitively.
No, well, according to our calculation, initially this part and the rest of the chain was entangled with 1/3, 1/3 times this log, blah, blah, blah. And this part is also entangled with this part with 1/3 times log, blah, blah, blah. And I get the same log, but now after this measurement, this part and this part is entangled with 1/6. So some part of, basically half of the entanglement was lost somewhere, which so I don't know quite why.
It is not crossing each chain, whatever the entanglement, it is not crossing that thing. That is I'm asking.
What do you mean by crossing?
Means A and A prime, A and rest has some entanglement. Then let's say that amount is alpha value. 1/3 it was. Oh, so it is not crossing. That's what you're saying. Oh, then it is fine. Yeah. 1/6 you are getting. I see. And another question is, why are you always performing Bell basis measurement? Why not some other measurement?
That may be interesting question. We have only so far done this particular setup, but if you have suggestions for some, so you are suggesting maybe more general measurements?
Yeah, because in the original picture, what you have shown there, it has been shown that if this part and this part is not maximally entangled, then some other non-maximally entanglement measurement can do better things. Actually. Such results are known.
Maybe you can suggest, because I'm very new to this field, so I would appreciate any suggestion. Yeah.
Okay.
Yeah. So, okay. So, this famous Holze-Larsen-Wilczek Calabrese-Cardy formula, to derive this, I don't need to assume anything about the CFT. Just for generic CFT, this works. But for this measurement-induced problem, I think we used a special property of free boson. And also that the measurement outcome can be replaced by some Dirichlet type boundary condition, which is particularly simple for free boson. So at least at present, I can say that this formula is only valid for free boson, and maybe at least for this particular setup. But for more general CFD, yeah, that's one of the things I want to consider. And my collaborators, Hoshino-san, did some numerical calculation Ising, but sometimes it doesn't look like a conform well, even conform well. So I don't quite understand why, but at least I can say that this Ising case, Ising is, you can say, is the simplest CFD, but once you apply replica trick, I have to deal with 2n copies of this Ising. Then problem becomes rather non-trivial, and sometimes it's very hard to calculate quantities. So yeah, so I have to say that so far the formula I showed you about this measurement-induced entanglement is only valid for free boson. I hope some generalization for more general safety, but right now I don't know.
Okay. Other questions, comments? So if not, let's thank Masaki once again.